Hey folks, today we're talking about algebraic limits. Some of these things we've hit before, but we're gonna just kind of pile them all into one big bag and talk about them all at once. So if I'm trying to find a limit without a graph or a calculator, I've got to use a bunch of algebra. So the best, simplest thing to do first is to direct substitute. Take whatever your limit is, plug it into your function, see if you get an answer. Corpy calls this, he says, never not first. Never not first. Well, if you're never not first, what are you? You're always first. So in other words, always try this first. Because what happens when you direct substitute, sometimes you get a hint, a big hint on what it means graphically when you plug in. So there's three scenarios. This is the one that, well, I'm going to highlight these. These are what we call the indeterminate form. This is an indeterminate form. I'm going to use that phrase quite a bit in this class. It means that we don't know what the value is, but it is a hint. We don't know what 0 divided by 0 is, but it is a hint. So we've got these scenarios. We've got when you have 0 over 0, what does that mean graphically? We've already talked about this. Well, hopefully you said that creates a hole. We also have where the numerator is not 0. If the top is not 0, but the bottom is, when you divide by 0, that's bad. What's the worst thing that can happen in algebra is dividing by 0. So that creates the worst thing that can happen in a graph, which is a VA. And then the last scenario is when you get a 0 on the top and not a 0 on the bottom. Well, if 0 is divided by something that's not 0, we get this thing called a 0. So this direct substitution would get you a value of 0. This direct substitution would tell you that the VA, and you could just answer D and E here, but on the multiple choice, I'll get into that later. But most of the time, you can answer D and E here if it's if it's a free response. But if it's a multiple choice, you'll have to do a little bit more work. And then if you get 0 over 0, then we get to do some algebra and try to figure out where that hole is and try to cancel it out. All right, so let's take a look. Can we direct substitute? Well, let's give it a try. I want to figure out what is cosecant. Cosecant of 5 pi over 3. Well, you can plug that in there. What I'm going to do instead is I'm going to think about cosecant in terms of its reciprocal. Because I don't really know much about cosecant. I just know that it's the reciprocal, not the inverse, but the reciprocal of somebody. Hopefully, you notice that it's the reciprocal of sine. So now I'm going to figure out what sine is at 5 pi over 3 and then reciprocal that value. So draw my little unit circle over here. 5 pi over 3, that's 5/60. 1, 2, 3, 4, 5. Take that triangle and blow it up. Right angle. My reference angle is a 60. Hopefully you can see that in there. Side lengths, this is negative square root 3 over 2. Points downward. And it's the long side across from the 60. This is 1/2. All right, sine is the same as y. So I would take negative square root 3 over 2 and I would reciprocal it, which would be negative 2 over root 3. If this is free response, you could stop here. If it's a multiple choice, they would never make it that messy. So I would then rationalize this, negative 2 root 3 over 3. So sometimes direct substitution works. That's the best, most wonderful scenario, because then we just can plug and chug and we done. All right, let's take a look here. I mean, pretty straightforward. Negative of negative 4. Now you might say we can't square root a negative, but what do these negatives do to each other? They end up canceling out. What's the square root of 4? Ends up being 2. Let me just do a quick review here, just as a side thing. Will you sketch this function? Just a real rough sketch. All right. Pause it if you haven't yet. Look, guys, you got to be able to sketch these pretty quickly. They should be coming to mind pretty quickly. So I'm looking at, first thing is the family. Okay, what family? We're the square root family. All right, so hopefully you thought that, whoosh. Hopefully you pictured that it goes like this. Then I think about this negative. Now, who's this negative with? This negative is with the x, which means it's going to do a horizontal. And it's a negative attached by mult. That's a horizontal reflection. So I'm going to take there's no shifts, there's no stretches, there's no shrinks. There's a pretty good sketch of square root of negative x. All right, that was just sort of a side note. All right, let's go. Knowing a VA exists. So what should, never not first, as Corpy says. What do we always try to do first? Plug and chug, direct substitute this value. And when I direct substitute, I get 1 cubed plus 1 is 2 over 1 minus 1 is 0. This is a VA. I know this is a VA because I've got a 0 on the bottom. I got a 0 on the bottom and a non-zero on the top. So if this is free response, you can write DNE and be done with it. If this is not a free response, you're going to have to figure out what the actual value is. And so the best way to do this is, look, you know it's going to be what kind of a value. It's going to be one of the infinities, right? It's either going to be going all the way up or all the way down. So I know it's going to be an infinity. To figure out which one, plug in something to the right of 1. If this was to the minus, you would plug in something to the left of 1. So let's plug in something to the right of 1, like 2. When I plug in 2, I get 8 plus 1 over 2 minus 1, which equals, I don't care what the actual answer is. All I care about is what kind of answer it is. 8 plus 1 is a positive. 2 minus 1 is a positive. A positive divided by a positive is a positive. So I know that's going to be infinity. Because if on this side, if this is going towards the positives, then everything is going towards the positive on that side of the asymptote. So it's actually really pretty easy. It's not too tricky to figure out which side or which infinity you're headed towards. Now you could also sketch this. When I did it, I did I did some long division to try to get an idea what the function looked like. But you don't have to do all that. We can just plug and chug, save ourselves a little time. All right, so let's start again. Let's plug in pi divided by plug in pi. What's sine of pi? Sine of pi is 0, so this is a VA again. If this is free response, I recommend just answering DNE and be done with it. If this is not a free response, which it probably wouldn't be that easy, you know it's going to be one of the infinities. All right, so I'm going to plug in. All right, now this is going to be interesting. Plugging in pi, you could plug in 4 if you wanted to, but I'm going to think about it as just like pi plus, I'm going to get rid of that, 0.1. In other words, I'm just going to move a little bit past pi. Now, how to do this, there's lots of ways to do this. If you were Mr. Wojo, he'd try to graph this thing. He'd graph the sine function and kind of think about those values. What I'm going to do is I'm going to use the unit circle. Okay, so first of all, if I'm plugging in pi plus 0.1 into x. So I would get pi plus 0.1 on the top over sine of pi plus 0.1. In other words, I'm just thinking about this as pi plus a little bit more. So if I go to pi, and then I go a little bit more, so here's pi, 180. And then I go a little bit more. I'm going to say that's my little bit more. What can you tell me about my sine value there? Take a minute, think it through, pause if you have to. What can you tell me about my sine value there? So I don't care what the actual number is. I'm just trying to get a sense of if this is positive or if this is negative. What's pi plus 0.1? That's a positive. Divided by what sine of pi plus a little bit more? That has a y value that points downward. That's negative. Positive divided by a negative is a negative. So now I know that my limit is going to be negative infinity. And I mean, here, let's prove it. I have not graphed this before, I promise. See, there you go. There's the proof. X over sine of x. Now, before I hit graph, I always want to check my mode. In my calculator, when I graph anything with trig, I want to make sure I'm in radians, always radians. All right, here's our picture. Oh boy, bad window. I'm going to adjust the window so that let's just go from negative 6.28 to 6.28. Then I'll be going a distance of 2 pi. And I'm going to count by pi's so that I know where, because I don't know where pi is. We want to approach pi from the right side. Okay, so there's pi right there. Coming from the right, where's our graph headed? Towards negative infinity. Perfect. Okay, so step back again. What's never not first? Always direct substitute, because that's going to give you a hint. Sometimes it works out. Yay, life is over. Good, or problem done. Sometimes we get a 0 on the bottom and a non-zero on the top. That's just DNE if it's free response, or the infinities if it's a multiple choice. Limits at infinity. These are also easy to figure out. They're easy to spot because it literally says as you approach infinity here. Now, this is one of those that are called rational functions. This is where I compare the leading to the leading. So who wins on the top? 5x squared. Who wins on the bottom? Negative 4x squared. And this is where I like to plug in the infinities. There's lots of different ways to do this. I like to plug in infinity. I just think it's fun to be able to plug infinity into something. What happens with those infinities? It's a tie. So we end up with, I like to bump the negative to the top. I shouldn't write equals. I'm going to use arrows. Negative 5 over 4. They're not really equal to each other. We're making all sorts of substitution. They have the same behavior. Ooh, this one's a little tougher. This one's a little tougher. I need to think about what the picture. I'm going to do this one by sketching. So I'm going to encourage you to pause here. See if you can give me a sketch of the natural log of absolute x. All right, if you haven't yet, I'm going to have you write a little note here. What kind of a transformation is this? First of all, is it around the function, the whole function, or is it around x? It's around x, which means it's a horizontal something. X moves horizontally, so any transformation to x would also affect it horizontally. Now, this is the one where horizontal, it's not a reflection. I call it a horizontal repeat. I don't know if that's a good way to say it, but it's a horizontal repeat. So what happens is I'm going to take the original function of natural log, pause, sketch natural log. Everyone should be able to do that. All right, let's see how you did. Natural log, boom. And, by the way, just as a reminder, this is the point. I'm going to do that in a different color. This is the point f of 0 equals 1. That's important. That's the only point that you really need to know. They don't expect you to know any other point except that one. Okay, so because we're doing absolute x, the positive x's become the negative x's. Now, it doesn't kill off the positive x's, but it makes the positive x's and the negative x's behave the same way. So this side of the graph is going to look at this. This is the only important point they expect you to understand. F of, I wrote that wrong. Go back over here. Good night. This is f of 1 equals 0. Sorry about that. So this is f of negative 1 equals 0. All right, so what's happening to our picture? So sometimes we got to sketch when we're looking at the infinities. That's why you have to know your parent functions. So as we head off towards x, as x heads off towards negative infinity, where does y head off to? Heads off towards positive infinity. So if it's limits at infinity, if they're polynomials, rationals, you can just kind of eliminate and look at who's the toughest on the top and on the bottom and compare them. If it's not, I recommend just making a sketch. Maybe I'll write a little note here on those two. I kind of like that. Compare versus sketch. Put those in parentheses. Looks cooler. Piecewise functions. So when you're looking at piecewise function, you're trying to evaluate a limit. First, just make sure that they're, oh no, we're not doing continuity. No, we're doing the limit. So all I have to do is I have to figure out, okay, what's the overall limit again? By definition, the overall limit is what happens to the one-sided limits. So if the one-sided limits are headed to the same place, then I have an overall limit. So I need to figure out the one-sided limits. So the limit of f of x as x approaches 2 from the left. All right, so which one of these would I plug into? If I'm approaching 2 from the left side, that means I'm coming from a little bit before 2, so I'm plugging it into this one. So I'm going to plug it in here, so I would have 2 squared minus 3. 2 squared minus 3 is 1. Then I would look at the limit from the other side. So I'm trying to prove the overall limit by looking at the one-sided limits. Now I'm going to pick a number that's a little bit bigger than 2, something on the right side of 2. So I'm going to use this as my interval. That means this is my function. So it would be 1/2 times 2 plus 1. 1/2 of 2 is 1. 1 plus 1 is 2. Game over. Game over. We would say the limit then would be d n e. Why? Because the limit of f of x as x approaches 2 from the left does not equal the limit of f of x as x approaches 2 from the right. What kind of a scenario is this? What does this look like graphically? Pause it if you haven't. Come on, what does this look like graphically? Hopefully you said this is a jump. We would say this is a non-removable jump discontinuity. All right, another piecewise scenario here. What would I want to do? I guess I could, I'm thinking I might want to try to sketch it. So, yeah, I guess I'll sketch it. All right. So here's my, all right, now I'm sketching the sine function. And the sine function lives everywhere where x is not pi. So whenever I sketch sine, I usually need 4 tick marks, with this one being 2 pi, which means that one's pi. So when my graph comes in and gets to 2 pi, there's a hole there. There's nothing there. So let's start to sketch this thing. Sine starts at 0. It goes up. It goes down. And at this spot, there's a hole because this graph does not live. This piece of the graph does not live when x is pi. And then the other side looks something like that. You know what I mean? And then at x equals pi, the actual value is at a height of 1. Now remember, we're trying to figure out the limit. Where is this function approaching? So from the left, the limit of f of x as x approaches pi from the left, well, I would plug it into this one. I guess I didn't even need to graph it. I guess I just wasted my time graphing that because I could just direct substitute. Because this is, if I'm not pi, if I want to pick something a little bit before pi, I would plug it into this equation. And if I pick something a little bit after pi, I would plug it into, this is just telling you where the point is. This is telling you what the graph is doing because this is what the graph is everywhere except at pi. So the limit from the left would be sine of pi. Sine of pi is 0. The limit of f of x as x approaches pi from the right is also sine of pi, which is 0. And since our one-sided limits are headed to the same place, the overall limit is 0. And if we look at our picture, that's exactly what our picture is doing, right? Our picture is approaching a y value of 0. Yeah, let's do the squeeze theorem. We've already done this one. It's pretty obvious when you're going to do a squeeze theorem. They give you this less than scenario. So how do you know when you're going to do squeeze theorem? If they tell you that a new function is between 2 other functions, I mean, that's how you try to recognize that. That's the dead giveaway. So these are usually pretty easy to figure out. I just have to figure out the limits of the functions that are given and show that they're the same, which means then this limit would be squeezed by those limits. So I would say the limit of natural log of x plus x squared as x approaches 1 would be equal to the natural log of 1 plus 1 squared, which equals, okay, this is what I was talking about over here. This is the one they expect you to know. Natural log of 1 is 0. Plus 1 squared equals 1. Then the limit of e to the x minus 1 as x approaches 1 would be e to the 1 minus 1. E to the 1 minus 1 is e to the 0, and anything to the 0th power is 1. So we've just shown that the limit of my first function is 1 at 1, and the limit of the second function at 1 is 1. So now I can do a squeeze theorem on it. So I have to establish that this function j of x is trapped between these other two functions. And I've already established over here that those limits are equal to each other, but I gotta still say it. The limit of natural log of x plus x squared as x approaches 1 equals 1, which also equals the limit of e to the x minus 1, comma. Okay, so I've established that this, I've got my the two requirements for the squeeze theorem. So now I've got to mention this squeeze theorem. Then by the squeeze theorem, the limit of j of x has to be equal to 1 as x approaches 1. We're going to use little write-ups like this quite a bit in this class, so try to get in the habit of wrapping your head around how we built those. All right, so factor out and divide. These ones are pretty obvious too. It looks like when you just kind of follow your math voice and you see, you look at it and you kind of think, well, that's a factoring problem. That's a factoring. These are factoring type scenarios. These aren't limits at infinity. If they're limits at infinity, we just compare leading terms, but they're approaching a value. So you're going to want to factor, clean things up, and see what you get left over. Now, I'll give you a hint on these. One of these tricks, well, first of all, never not first, plug in. So 2 squared is 4, 4 minus 4 is 0, 2 minus 2 is 0. So I know I've got a hole here. Now, this one you could probably just factor and go from there. But what I want to point out is this is the hole. We know that's the hole because when we plug in 2, that's what causes the 0 on the top and the 0 on the bottom. So in a sense, I already know that this on the top has to have an x minus 2 in it somewhere. And I'm going to show you over here how we can use that trick to figure out something that we can't factor in our head. Well, maybe we can if we remember that there's that poster in my room. All right, so I factor. This is a dopes, difference of perfect squares. My x minus 2's cancel out. That means I now can direct substitute. 2 plus 2 equals 4. All right, so this is what I'm talking about. Let's look at this one. So I've got this problem here. This is the hole. I know that the top also has to have x minus 1 as a factor. If it didn't have x minus 1, we wouldn't. Oh, I forgot to plug in for never not first. 1 cubed is 1. 1 minus 1 is 0. 1 minus 1 is 0. So I know I've got a hole. If this is a 0 on the bottom, then that piece must belong to the top. So what I'm going to do here is I'm going to do a long division. Now, you wouldn't probably think to do this, but that's why we show it to you so that you can try to recognize it more and more. So I'm going to do a synthetic division on this. So this is doing the dividing. So this goes in the house. So that's a 1. And remember how this works. I list all the coefficients. So that's 1x cubed. That's 0x squareds. That's 0 x's and then a minus 1. So what I'm saying here is I already know x minus 1 has to go into this. What I'm trying to figure out is what's left over when I factor out that x minus 1, and I can do that by synthetically dividing. The 1 drops. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1, and negative 1 plus 1 is 0. That's good, because that means that x minus 1 is truly a factor. Okay, so this thing was an x cubed. We broke it down by an x, which means we're left with 1x squared plus 1x plus the number 1. Pretty slick, huh? So if I know that that's the whole, then I can long divide or synthetically divide this thing, cancel out that whole, and then I can direct substitute. 1 squared plus 1 ends up being 3. Let's see if you can do that on the, well, I'll give you a hint first. This one's a little bit more complicated, so I'll give you a hint first. Look at the denominator. What is your math voice saying in the denominator? Oops, shoot, never not first. I always forget to do that. And I wish I didn't, because I get so excited about showing how to do these. Okay, so let's take a look here. So I'm going to go ahead and plug and chug. So that would be negative 1 to the 4th would be 1. Negative 1 to the 3rd would be negative, which is going to change that to a positive. Negative 1 squared would be positive with a negative. Negative 1 times negative 3 is positive 3, minus 4 ends up being, that's 2, take away 1 is 1, plus 3 is 4, minus 4 is 0. So I have a 0 on the top. Let's plug in this to the bottom, over, that's 2 times negative 1 squared would be 1, minus negative 1 would be plus 1, minus 3. 2 plus 1 is 3, 3 take away 3 is 0. So we do have a hole somewhere. Now we've got to figure out where that hole is. So when we plugged in negative 1, we knew that this created a 0 on the bottom. And we know that it created a 0 on the top. But on the top, I don't want to try to factor this. That's a mess to try to factor. So let's try to factor the denominator, which is much easier to factor. I'm going to encourage you to pause here and practice your factoring. All right, let's see how you did. So I know it's going to be 2x and x. 6, that makes negative 1. That's a 2 and a 3. So the 3's got to go here. The 1's got to go there. I need to be a negative 3 and a positive. Now I always distribute to make sure. 2 times 1 is 2x squared. That's 2. Take away 3 is negative 1. Negative 3. Yep, we got it. All right, now, who is the problem here? Which one is causing us the issue? This is the whole. How do we know that? Because when we plug in negative 1, it's going to create a 0 on the bottom. And if I plug negative 1 into this, it doesn't create a 0 on the bottom. So that means that this has to be able to divide into this. X plus 1 has to divide into this quartic. So I'm going to do my little synthetic division down here. Negative 1. Coefficients are 1, negative 1, negative 1, negative 3, negative 4. The 1 drops. That's negative 1. That's negative 2. That's 2. That's 1. That's negative 1. That's negative 4. That's 4. That's 0. So that means that my numerator now is x plus 1 times, I'm going to have to write it way up here. I know it has an x plus 1 because we just divided it into there and got a remainder of 0. This was an x to the 4th, so this would become x cubed minus 2x squared plus x, subtract 4. These guys now cancel, and I can finally direct substitute negative 1 into this. So it would be negative 1 cubed minus 2 times negative 1 squared plus negative 1, subtract 4, over 2 times negative 1 minus 3. So what's that? Negative 1, that's positive negative 2, minus 1 minus 4, over negative 2 minus 3, minus 2, minus 2, minus 4, minus 2, minus 8, over minus 5. Negative over a negative is a positive. We get 8/5. Woo! That's a beauty. That is a beauty. All right, so this is it for this one. See you in a few.